Hey everybody, welcome to Math with Ace. Focusing on statistics today, we are going to be talking about a different type of hypothesis testing, which we call the chi-square goodness of fit. Some people might read that as chi. It is called chi. And the chi-squared test statistic is using the Greek letter chi, which looks like an X. And so chi-squared goodness of fit. We have worked on hypothesis testing in the past where we worked with means versus proportions. Chi-square is used for categorical data that has more than two proportions or more than two categories that we're dealing with. So we had one proportion and then we did two proportion, and now we're doing more than two where we have multiple categories that we're dealing with. A chi-square distribution is always going to be skewed to the right. It is not symmetrical. It does not look like a normal distribution, and it depends on the degrees of freedom. So your degrees of freedom is going to dictate, just like in a t-distribution, each different set of degrees of freedom is going to have a different curve. So your initial curve maybe looks something like this, but then as your sample size increases or your number of categories actually increases, you get more of a skewed distribution to the right. And let's say maybe it's actually more like that, maybe a bigger hump, but it is dependent on your degrees of freedom. And the way in which you calculate degrees of freedom is you take k minus 1. In the past, we've used n, where n represents the sample size. Here, k is the number of categories. So we're not saying we have a random sample of 250. We're saying maybe we have a random sample of 250, but we are dealing with however many categories that we are talking about in the chi-square distribution. Because of the way that the distribution is shaped, the chi-square test statistic is always positive. So you will always have some value greater than or equal to 0. So it's always a right-tailed test. Now, the way that we write our hypotheses doesn't necessarily use the symbol greater than. We will typically write our symbols using, we'll say maybe words for the null and the alternative. There is a way to use symbols in the null hypothesis, but typically the alternative is going to be in words. So I'll show you both of those. The test statistic, the way that we calculate chi-squared. So in the past with proportions, we've had the difference of the null and the difference of the hypothesized value and the sample value, and then divided by the square root of the hypothesized value, successes and failures, and sample size. The way that the chi-squared test statistic is calculated is you are going to sum every single observed value subtract the expected value, square that to make it positive, and then divide that by the expected value. Well, what is the observed value? What is the expected value? It all comes from the data. And so your observed value is the raw data that you're given to analyze, and the expected value is based on what you would expect, assuming that the null hypothesis is true. So let's get together an example so we can talk about this. Okay, we're not going to do a full hypothesis testing here, but we are going to talk about how we would set up the null and the alternative, as well as calculate the expected counts and the test statistic so that we can then go on and do a full example. So this question says, a researcher claims that people's favorite type of exercise differs from what was suggested in a national fitness survey, which said that running was 35%, weightlifting was 25%, yoga and Pilates was 20%, and other was 20%. So it's saying that we have this assumed distribution. And so to test, they randomly selected 500 adults, which found that running was 160 for those 500 adults, 110 for weightlifting, 130 for yoga, and 100 for other. So if we wanted to test a claim, we need to figure out how do we want to write this. We could write this using symbols, which some people do, where this is the proportion of running, this is the proportion of weightlifting, this is the proportion of yoga or Pilates. and this is the proportion of other, not a Y, proportion of other, where the proportion of running was 0.35, weightlifting was 0.25, yoga Pilates was 0.2, and other was also 0.2. So in your null hypothesis, you could say PR equals 0.35, PW equals 0.25, PYP equals 0.2, and P of other equals 0.2. And then the alternative is that at least one of those proportions is different. That's using the proportions that are given, and then our alternative is that at least one is different. Another way to do this is to just use words for both, which is the direction that we will go for our examples. So the null hypothesis would be that the distribution matches what the National Fitness Survey says. So the distribution of exercise preference is the same as the national survey. So we are assuming what they are stating to begin with. We have that null hypothesis as initial assumption, and then the alternative would be that the distribution of exercise preference is not the same as the national survey. Just like with previous hypothesis tests, our null hypothesis is always a statement of equality. And so we're saying it is the same. And then the alternative is that it is not the same. So that's how we set up our null hypotheses and our alternative. How do we calculate expected counts? In order for the large condition to be met with chi-square testing, our expected counts need to be at least 5. Random and normal conditions are as they are in all of the other ways that we check. But for the large counts, that's why we don't call it normal. It's the large counts condition. Our expected counts need to be at least 5. Well, what do we expect to happen for these 500 adults if it really is 35%, 25%, 20%, and 20%? So we need to calculate what we would expect. So we have these categories of what we would expect: the running to be 35%, weightlifting to be 25%, yoga Pilates to be 20%, and other to be 20%. And so if we expect those to be true, then we need to figure out what is 35% of 500. So we would take 500 times 0.35, and that would give us 175. So if it really was 35% of those 500, we would assume that 175 would prefer weightlifting, assuming that the null is true. For the 25%, we do the same thing. We multiply 500 times 0.25, and we get 125. For the last two, 500 times 0.2, 500 times 0.2, we get 100 each. Now, all of those should sum to 500 because that's how many we have. But each of these is at least 5, so the large counts condition is met. So what you do to calculate your expected counts for chi-square goodness of fit is you take your sample size and multiply it by whatever the proportion is for each of the categories. Sometimes it's like an equal split amongst 5 categories. So in that case, you would do 500 divided by 5. It depends on the information that you're given. Now, notice here we have running, weightlifting, yoga Pilates, and other. That's 4 categories. So our degrees of freedom here is 4, -1, or 3. So when we go to do a chi-squared test statistic, we are going to use a degrees of freedom of 3. All right, how do we calculate the chi-squared test statistic? You can use Statlet, but when we're doing this, sum of the observed minus the expected squared divided by the expected. The observed is the raw data of what actually happened. How many people preferred weightlifting? How many people preferred running? And so on. And the expected is what we just calculated. Okay, so I wrote these here: running, weightlifting, yoga, Pilates, and other. What we're going to do is we're going to take running, which was 160 observed from the chart above, minus 175 is what we expect, squared over the 175 expected. So you see that number twice. We're going to add that to the 110 weightlifting minus the 125 we expect, squared over 125, plus 130 minus the 100 we expect, squared over 175, plus the 100 other minus the 100 we expect, squared over 125. 160 minus 175 is -15, which we're going to square. 110 minus 125 is also -15, which we're going to square. 130 minus 100 is 30, which we're going to square. Sorry, this should be 100. Plus 100 minus 100 is 0, which we're going to square. -15 squared is 225 over 175. 225 over 175, 900 over 100 plus 0. And so in this case, I could find a common denominator, or I could just go ahead and add them together. So 225 divided by 175 plus 225 divided by 175 should not be dividing by 175 here. This should be 125. So 225 divided by 175 plus 225 divided by 125 plus 900 divided by 100 is 12.086. So the chi-squared statistic is 12. So that is how far off each value is on average from what we would expect. So then we would use Statlet to calculate the probability of that occurring and make our conclusion based on a p-value as we have done in the past. So let's head on to the next video and watch an example.